Physical Comp, and here's my video lab report for Physics 2211. The lab will observe the motion of an object at a constant velocity without change in direction by comparing the motion of a whiteboard marker against a computational model of the same whiteboard marker. The two models will provide an idealized and realistic simulation of Newton's first law of motion. Every object will remain at rest or in uniform motion in a straight line unless compelled to change its state by the action of an external force. We can manipulate this law to predict the location of an object with a constant velocity using the momentum update formula. Additionally, we observe Newton's second law of motion. Force is equal to the rate of change of momentum. For constant mass, force equals mass times acceleration. Our lab procedure includes establishing the experiment system and surroundings, recording of the system's motion, and the graphing of two models' motion onto a plot. It is important to note here that we assumed a lack of air resistance and frictions in both models. In both models, the marker makes up the system, while the surrounding is everything else captured in the model. In our physical model, we use the provided lab space and our phone to record the motion of the marker. We then use Tracker, a free online application, to generate data points from the marker's motion. And we finally plotted the data points onto a graph to analyze and make conclusions. The computer model starts the marker with an initial constant velocity calculated from the physical model's data. We did this calculation by determining the length the marker traveled over the time it took to travel that distance. Computational model's initial and constant speed was determined to be half meter per second. We also set the origin as its starting position because the starting position had no impact on the overall velocity and distance traveled by the computational model. We programmed our computational model to these standards by updating the starter code. We only changed the position update code as the constant velocity meant that the position was constantly changing. However, we did not affect the velocity update code as there was no acceleration in this constant velocity model, nor did we touch the position. Plugging the velocity into the starter code, we ran our new program and collected the data points. We finally graphed the computational data against the physical model to further analyze the two. After plotting the models onto a graph, we see that the physical and computational model are now extremely alike. The only difference between them is that the physical model starts to slow down. This is due to air resistance acting against the marker's motion, slowing down the motion as Newton's second law stated. However, both models maintain a constant velocity during the time period, since no outside force significantly acted against them, reaffirming Newton's first law. Computational and physical models acted as predicted. There were no discernible errors in our observations. Now what if, during the experiments, the direction of the x-axis were switched? The only difference would be in the horizontal direction of the linear plots of data. Instead of heading to the right direction, the plots would instead head to the left direction. The conclusions would stay the same. Both models would demonstrate Newton's first law of motion, while the physical model will show Newton's second law of motion. Finally, using our data, could we predict the number of pushes and pulls or the number of forces acting upon our models? While the physical model had an innumerable amount of tiny forces acting against it in the form of air resistance, the computational model had a net force of 0. This doesn't mean that no force was acting on the model. In fact, an infinite combination of forces could act upon the model as long as they cancel each other out, meaning that even with a zero net force on an object, we could not predict the number of pushes and pulls.